Let us talk about this problem. Count set bits in an integer. We are given a non-negative integer, an integer which is either 0 or any positive value. We need to count how many set bits it has in its binary representation. For example, 5. If we have n equal to 5, then its binary representation is going to be 101. If your number is stored in 32 bits, then its actual representation is going to be 29 0 bits, right? 29 leading 0 bits and then 101, right? 1 plus 4, 5. So this is the actual binary representation of this n equal to 5 if it is stored in 32 bits. So you have 29 bits as 0 and then last 3 bits as this. If it is stored using 64 bits, then first 61 bits will be 0 and last 3 bits will be 101. For n equal to 7, our binary representation is last 3 bits 111 and first 29 bits 0 if it is 32 bit, right? For n equal to 13, our binary representation is 1101, 8, 4 and 1. These 4 bits are the last bits and then first 28 bits are 0. So we are given a number. We need to consider its binary representation. We need to count how many set bits it has in its binary representation. If you look at 13, it has total 3 set bits, right? 1, 2, 3. That is why our output is 3. Now please pause this video and try to write down a program for this. We are going to discuss 3 different solutions of this problem. Let us first talk about the naive solution. The naive solution is you check the last bit. If the last bit is 1, you increment the result, then you remove the last bit. When we say remove the last bit, we mean we make one leading bit 0 and we simply ignore the last bit. Let's see what do we mean by remove the last bit. So we have, say, number 5. Its binary representation is this. If it is 32 bits, then 29 zeros and then 1. We figure out last bit is 1. We increment the result and then we remove this last bit. So these are 29 0 bits. And now what are we going to do? We are going to make these 30 0 bits. And then we are going to have 1 0. So we simply removed it. And now we'll check if its last bit is set or not. If its last bit is set, then we'll increment the result. It's not set, then we do not. So it's not set, we do not increment the result. And we remove the last bit also. So these were 30 bits, that was 0. Now we'll make them 31 bits, which are 0. Right, so these are 31 bits. We mainly remove this last bit. And now we are going to consider this bit. This is 1, so we'll increment the result and then we'll remove this last bit. So we'll have all the 32 bits 0. So when all the 32 bits are 0, your value is going to be 0. So you will stop at this point. So let's write down the code together. We'll run a loop that will run until your n does not become 0. So we'll say while n is greater than 0. And what are we going to do inside this loop? We are going to check if the last bit is set or not. So one simple way to check whether the last bit is set or not is simply do this. If n %2 is not equal to 0, then our last bit is set. We increment the result plus plus. So this is how we check if the last bit is set, then we increment the result. We also need to remove the last bit as we did here, right? We remove the last bit, then we remove the last bit. So how do we remove the last bit of a number? There can be multiple ways. One simple way is to do n equal to n by 2. Right? You simply make 5 divide by 2, you will have 2. Then you do 2 divided by 1, you will have 1. And 1 divided by 2, you will have 0. right? So you simply do n equal to n by 2. We can also use bitwise operators in place of these. We can write this as if n and 1 is equal to 1, right? If this is the case, then do result plus plus. And we can replace this using right shift. N equal to n by 2 can always be achieved by right shift. So you can replace this if condition with this condition, and you can replace this particular expression is n equal to n right shift 1. So this will also do divide by 2. Your 5 will become 2, then 2 will become 1, and then 1 will become 0. This can in fact further be simplified. You can simply do result equal to result plus n and 1, right? So you are doing a bitwise AND of n with 1. What is the binary representation of 1? It has 31 bits as 0, and then it has last bit as 1. If you do bitwise AND of this any number like 5, if I write the binary representation of 5 here, I'll get 1, 0, 1. And if I do bitwise AND of these two numbers, this represents 5 and this represents 1, I will get 1. All the preceding 31 bits are going to be 0. Because we are doing bitwise AND, we have 0 in one number, so we are always going to get 0. So our bitwise AND of any number with 1 is going to be 1 if that number is odd. It's going to be 0 if that number is even. So that is why we can simply add n and 1 to result, and we get the result incremented only when n is odd, only when the last bit is set. So this is a naive solution. So how much time it takes? It takes time proportional to total bits in binary representation of n. If it's 32 bits, then it's proportional to 32. If it's 64 bits, then it's proportional to 64 bits. So the time complexity of the solution is theta of total bits in n. That's the time complexity of the solution. This is naive solution. Now we are going to talk about two more solutions, where one solution is called standard algorithm, Bryan-Kernighan algorithm, and that solution is going to take less than this time. And then we will talk about third solution, which is a constant time solution. Let us now talk about Bryan-Kernighan algorithm. This algorithm takes time equal to set bit count. So if your number has only 2 set bits, then this loop is going to run 2 times only. And if your number has 4 set bits, then it's going to run 4 times. If your number is 40, initially this is your binary representation. You have bit set for 8 and then 32. After first iteration, this bit is going to get off, right? And it's going to become 32. After second iteration, this bit is also going to get off and it's going to become 0. And when it becomes 0, you are going to stop. So how is this magic happening? That this algorithm requires time which is set bit count proportional, not the total bit count proportional. The main part here is this expression. Let us see how does this expression work. So in this diagram, I explained this expression. We have n is equal to 40 initially. So this is binary representation of 40. Here I have ignored the leading 0 bits, right? You can assume that if the number representation is 32 bit, then the remaining bit on the left side are 0, right? So how many remaining bits we have? There are 6 bits, so you will have 26 0 bits on the left side. Okay, so we have a number n equal to 40. Let's see what happens when we do this operation on this number. So in this operation, first we are computing n minus 1. So this is 39. And then we are doing AND of these two numbers. So we get 32 as a new value of n. And what happens in this operation? You get the last bit turned off. Initially your number was 40, now it becomes 32. Your last bit is turned off. And how does this happen? When you subtract 1 from a number, all the bits which are 0 after the last set bit, they become 1. And your last set bit becomes 0 from 1. When I say last bit set, I mean the leftmost bit set, right? This is the leftmost bit which is set in this number. This bit becomes 0 after doing n and n minus 1. So we get this result. Again, we have one more bit set. So that's the only bit set, and that's the last bit set or leftmost bit set. And if I do n minus 1 end with this number, n minus 1 is 31. If I do end of these two numbers, I get 0. So in every iteration, you are turning off the last set bit. And that's how this algorithm gives you the total set bit in the given number. Because it's one by one turning off the last set bits, and it's going to stop when your number becomes 0. It becomes 0 here, so it stops here. So it ran 2 times, and you have 2 set bits in the number 40. Let us now talk about a lookup table based method to count set bits. This method requires theta 1 time to count set bits. It's better than the previous 2 methods. However, it requires some pre-processing. So the idea is this. We divide our input 32-bit number into 8-bit chunks. So there are 4 chunks. So 8-bit means you have numbers from 0 to 255. When you have 8 bits, what is the range of your numbers? From 0 to 255. Simply 0 to 2 raised to the power 7 minus 1, right? So these are the numbers that you can represent with 8 bits, 0 to this, right? Which is 255. So you mainly need count set bits lookup for numbers from 0 to 255, because you divide it into 4 chunks and you are going to count set bits in individual 4 chunks one by one. So here we do this pre-computation, which is done first, so that all the count calls after it can happen in theta 1 time. And what do we do in this pre-computation? We make a table of size 256 here, and then we fill this table in such a way that table I represents the count of set bits in number I, right? So table 0 is going to be 0, table 1 is going to be 1, table 2 is going to be 1, table 3 is going to be 2 because 3 has 2 set bits. Table 4 is going to be 1 because 4 has 1 set bit. So we need to fill these values in this table so that in big O of 1 time or theta 1 time, we can find out how many set bits a number has. A number which is having range from 0 to 255. And how do we fill this table? We fill this table in bottom-up manner. We initialize the table 0 as 0. Then we fill the remaining table using the pre-computed results for I by 2. You remember the naive method, right? What we were doing in the naive method? We were checking the last set bit. So we first check the last set bit and then we reuse the result that we have computed for the number I by 2. So for example, if I is 5, you are computing for I equal to 5 currently. You will check I and 1, you will find this value is 1. And then you will use the previously computed result for table of 5 by 2, which is table of 2, right? So this is how you will get 1 plus 1. Table 2 will give you 1, table this will give you 1, so you will get 2. So this is how we fill this table, and this table works for an input number which has value from 0 to 255. Now how do we handle 32-bit numbers? We take our input number, we find out what is the value of last 8 bits. So if you take a closer look at this operation, what are we doing? We are doing bitwise AND of our input number with FF. FF is hexadecimal representation of 8 set bits, right? So you take the last 8 bits of this number, right? And you find out their values and you use that value as an index in the table array. That is how you count how many set bits are there in the last 8 bits, right? After that, you shift the number by 8 bits. So you ignore the last 8 bits. You simply remove them and shift the number by 8 bits. So next time you get the count of set bits in the next 8 bits. So first you get the count in the last 8 bits here. by doing with 0xFF. 0xFF is nothing but all ones. So you have all ones in this number. When you do bitwise AND of these two, you will get 13 only, and equal to 13, right? This is the value of last digits. See, this here you are getting 13, but suppose your number was bigger than 255. Say it was 256, then you would have got 0 here, right? Because this number 0xFF has last 8 bits as 1 and all the other bits as 0, 0, 0, right? So what it is going to do, it is going to make all the bits 0 in the result, and it's going to consider only the last 8 bits. So you're getting 13 here, but suppose if the number was greater than 255, if it was 256, then you would have got 0 here. If it was 257, then you would have got 1 here. So you basically get the value of last 8 bits in the binary representation by using this expression. And then you do a lookup of this value in your table and you get the count of set bits in those 8 bits. This is how you initialize the result. Then what you do is you move these 8 bits ahead, right? So this, your number which is represented this way, changes to this thing. These 8 bits are gone and these 8 bits are copied here. Here you have 30, so all the bits are now 0, but whatever was there would have come here, right? After moving the next 8 bits, we count set bits in those 8 bits. Then we again move 8 bits so that we have the next chunk at the end and previous bits at 0, and we count set bits in that chunk of 8 bits. And after moving that chunk and counting set bits in that chunk, we move the last chunk of 32-bit numbers. We move the last chunk here and we count the set bits in that chunk. And we add all these set bits to the result one by one. So we have total count set bits in the overall number. If you want to extend this solution for 64-bit numbers, you will just have to do it 4 more times, right? And you can use the same function here. And here you are doing it 4 times, then you will do it 8 times. So this is a lookup table solution that works in theta 1 time under the assumption that you've already done these computations. You've pre-computed this table. Now all calls of count set bits for all the numbers now work in theta 1 time.